Okay, so good evening, everyone. Welcome to the NPTEL online certification course on water and wastewater treatment. And we are in week 2 now. As you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee. And I am Akash Saha, one of the teaching assistant for this course. And I am a PMRS scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. Okay, so as we have seen the basics of water and wastewater treatment in the previous class, we will be moving forward in the same direction, and we discussed about the mass balance thing. Okay, in this week's lecture we discussed about various type of reactors, starting with the batch reactor, the CSTR, which is the continuously stirred tank reactor, and the PFR, that is the plug flow reactor. And then we made a comparison between all those reactors, what are their volumes, how to calculate the HRTs, okay, what are the different reaction rates, all those things. And we also have seen some non-ideal systems. Okay, so we derive the systems based on ideal conditions, but when it is not ideal, so how can we move forward? So we have seen those things based on Pecklet number and all. And then we have seen the water quality parameters. So we started with basic BOD and COD, like the biodegradable or the biochemical organic oxygen demand and the chemical oxygen demand. Okay, and then what is the dissolved oxygen and what are the different ways to measure it, and then the nutrients in water. And we'll be moving on with the other water quality parameters in the upcoming weeks. Okay, so let's see and try to solve some problems based on these topics which we have discussed in week 2. So okay, this is the first MCQ problem. So it says that in a CSTR, that is a continuously stirred tank reactor, which assumption is made about the concentration of the reactor, concentration in the reactor. Okay, so whether it varies with the distance in the reactor, or it is constant and equal to the influent concentration, or is it constant and equal to the effluent concentration. So please try to answer this question. You can use the chat box to give the correct option, A, B, or C. Then we can discuss about the answer. Or you can unmute yourself and give the answer. That is also an option. Okay, so someone has answered it as C. So we are talking about that whenever uh, suppose something is none. Okay, so the question is like, suppose we are inputting something into the reactor. So what is the concentration? Okay, is it varying B or is it constant? Okay, and if it is constant, whether it is equal to the influent concentration or to the effluent concentration. Okay, so just to give you a context, because all of you are giving different answers. So uh, so basic schematic of a CSTR, if we see, so suppose this is the reactor. Okay, it is generally a closed reactor. Suppose some inflow is coming, maybe the flow rate is Q in, okay, and the concentration is C in, okay, and inside some reaction is going on, maybe first order, zeroth order, second order, any reaction is going on, and after that there is some effluent. Okay, so that effluent that is coming out, the discharge may be Q out, and the concentration is C out. Now inside this reactor there will be some concentration C. Okay, we don't know what is the concentration. So now in this question it is asked that in a CSTR type of reactor, okay, so it is continuously stir tank reactor. So what about this C? What is this C equal to? Is this C varying with time, increasing, decreasing? We don't know. Some variation is there, or is it equal to the input concentration, that is the C in, or is it equal to the output concentration, that is the C out? So this is the question. So this is an assumption rather that we make while designing this reactor. So now you try to answer this.
In the both case same way too. C in and C out.
No, not necessarily, because see the scene. Suppose we take the case of BOD. Suppose we are inputting 100 milligram per liter of BOD. So
Okay.
that would be my Cin. Now in the outlet, I want that BOD to decrease, right? That's why I'm going through the reaction. If the input and output concentration is same, then why we are running this reactor? What is the point? So suppose this
Okay.
C out is maybe 10 milligram per liter. So what do you think the inside concentration would be? Any idea, any rough guess? What do you think? What should be the concentration? Should it be more than 100, less than 100, or it would be varying with time, or what? So most of you will have the thinking that it must be varying, right? If it is inside the reactor, the concentration must be varying, and after a particular point, we will take out this. But you should keep this in mind that all these things are derived at some steady state condition. Steady state condition. What do you mean by steady state condition? Is that the concentration or any parameter is not changing with time. Steady state, it is means there is no variance in time. So with time there will be no variance, it will achieve an equilibrium, and the concentration with the will be same. Now talking about the concentration inside, whenever something is coming like Cin is getting into the reactor, it will directly go to the concentration of the effluent. Okay, if it has reached the steady state concentration, okay, the reaction will be such, or the concentration will gradient will be developed such that this C concentration inside the reactor will be equal to my C out, so that we can take this out. Okay, there will be some uh, retention time for this process to go on, but once it has achieved the steady state concentration, the concentration inside the reactor will be equal to the concentration that is coming out as effluent. Okay, so the answer will be, and mind you, it's a well mixed reactor, everything is getting mixed properly. There are we are thinking that there are no dead zones. Okay, so nothing is there, so it's a well mixed reactor. So the correct answer should be it is constant and equal to the effluent concentration. Am I clear? Is there any doubt? Anyone having any doubt for this? Okay, so while designing any reactor, we must know the assumptions of the designing of the reactor. So if you see the detailed solution, I have uh, pointed out a few key assumptions. So first assumption is there is perfect mixing. That means the contents of the reactor are assumed to be perfectly mixed, meaning that the concentration of the reactants and the products is uniform throughout the reactant at any given time. So it is not changing with time. Then outlet concentration. Outlet concentration will be equal to the reactor concentration. So that's what I was saying, that C is equal to C out. Right? C out. Yeah. So since its perfect mixing is assumed, the concentration of the species in the outlet stream is same as the concentration inside the reactor. Now the next, steady state operation. Okay, so unless specifically mentioned that it's in transient state, that is the changing with time, a CSTR is typically assumed to be operating at steady state, meaning that the concentration inside the reactor does not change with time. That is, the change in concentration with the change in time, dC by dt will be equal to zero, right? Then constant density. So this is for any liquids, we are assuming that the density will not change. So it will be the mass balance calculations will be certain. And the last thing is instantaneous mixing of the incoming stream. As I told you, whenever the scene is coming into the system, the entering feed stream is assumed to mix instantaneously with the reactor contents upon entry, meaning that there are no concentration gradients inside the reactor. Right? So these are the 5 basic assumptions for the designing of a CSTR. Is there any problem for any of you? I hope it is clear. Okay, we'll move forward. Okay, next question says, compared to CSTRs, plug flow reactors are typically dash in their removal efficiency for a given compound. So we have to compare between a plug flow reactor and a CSTR, whether it's less efficient, more efficient, or equally efficient. So what do you think? I think in the last class also I have discussed a similar kind of question. Okay, more efficient. Any other answer? B, more efficient. Okay, so all of you are answering a more efficient. That is the case because plug flow reactors due to the concentration. So in the last thing we have discussed that there is no concentration gradient, right? But in a plug flow reactor there is always a concentration gradient along the flow. Okay, along the length of the reactor there is a concentration gradient due to which it is found to be more efficient, right? So the same thing I have written here. So the reactants flow in the reactor in a plug flow manner. Okay, so you can consider each of these units as a CSTR. Some n number of CSTRs, if we mix combine together, it will form a plug flow reactor. And within each CSTR, there will be no concentration gradient, but throughout the flow there will be a concentration gradient, and it also avoids back mixing. Okay, so there is no mixing in the backward direction, everything moves forward. So this is the reason why plug flow reactors are found to be more efficient than the continuously stirred tank reactors or the CSTRs. Okay, I hope it is clear because direct question. If you have any confusion at any point of time, please unmute yourself, stop me, and we can discuss. Next problem. The fundamental mass balance equation relates the rate of accumulation or lessening of a compound to its rate of removal, rate of formation, rate of removal, both A and B. So we are talking about the rate of accumulation or depletion or lessening. Okay, so what does it depend on? Does it depend only about on the formation, rate of formation, or on the rate of removal, or both of them? So I got one answer as C. Anyone else? Any other opinion? Just think about fundamentally. Okay, so a similar analogy will be if I want to know the population increase of a certain place. So rate of increase or rate of decrease in population. So what does it depend on? Whether it will depend on both the rate of births and rate of deaths, okay, or both of them or any one of them. So a similar analogy can be used on these terms. So as most of you are answering, it will depend on both of them. Okay, so both A and B are correct answer. And if you see the general mass balance equation, so dm by dt will be equal to the rate of input. So not only the rate of formation and removal, that is, if I say the rate of births or rate of deaths, there is a rate of input and rate of output also. So input and can be some people migrating from one place to other place. Okay, so how many people are coming into the city and how many people are moving out of the city. So rate of input and rate of output will also govern my rate of accumulation or lessening. Okay, so similarly, we can say this where, so in this formula, M denotes the mass of the compound and dm by dt is the rate of accumulation if positive or depletion if negative. Okay, or lessening as mentioned in the question. So this equation can be applied to any batch reactor or a CSTR or PFR. So any control volume, any specific area, we can see what is the change particularly happening to a particular mass. Okay, whether it is increasing or decreasing based on the input, output, formation and removal. So four things we have to check, right? I hope it is clear. We'll move forward. Nutrient enrichment or eutrophication in water bodies can lead to increased biodiversity and fish populations, harmful algal blooms and ocean and oxygen depletion, improved water clarity and recreational value, none of the above. So what would happen in the case of eutrophication? So can someone tell me what are the typical nutrients which are causing this eutrophication? What are these nutrients? Examples?
Like nitrogen and phosphorus.
Yeah, definitely. Nitrogen and phosphorus. These are the main nutrients. Yeah, right. So what do you think will happen in the case of eutrophication? Option B. So it is said to uh, cause harmful algal blooms. As you can see, a thick sheet of green colored mat over the ponds or lakes, wherever. So those are nothing but algal blooms. And what will happen due to them? Oxygen will get depleted. How it will get depleted, we'll see. We'll see how it is getting depleted. So basically, so the first thing is if excess nutrients are present in any water body or any water system. So we can see that rapid growth of algae, okay, leading to algal blooms will happen. And some of these algae are like cyanobacteria, which are called the blue-gill algae, can produce some more toxins, okay, which is harmful to the aquatic life. So there will be a decrease in the biodiversity, not increase in the biodiversity, there will be a decrease. So this is the first problem. And this algal bloom, because there is a thick green mat over the surface, it will block the sunlight, it will disrupt the ecosystem, aquatic ecosystem, and it will harm the submerged plant. So this is one criteria, one part. Other part is this algal will uh, eventually die. Okay, they will eventually die. They will go to the bottom and start decomposing. And during this decomposition, this will be carried out by the bacteria. So, okay, so while these are getting decomposited, okay, they will use up the oxygen in the water system, due to which hypoxia or anoxia, which is nothing but low oxygen level or complete oxygen depletion, will happen, and it will create some dead zones where the marine life cannot survive. So very simple thing, which we all know in general. So these are the two main problems due to the nutrient enrichment or eutrophication. Right. Next part. Next question. What is the primary concern associated with high nitrate levels in drinking water? Okay, so we have to find out the primary concerns related to the high nitrate level in the drinking water. So whether it is algal blooms and taste and odor issues, increased corrosion of water pipes, blue baby syndrome in infants, or all of the above. So we are talking about high nitrate levels. So just think in terms of nitrate. Okay, don't bring the nutrients, the overall nutrients into the picture, which we discussed in the last question. Just think in terms of nitrate. If there is too much of nitrate in the water, what would happen? So if you are thinking only in terms of nutrients, yeah, algal bloom is a possibility. But due to high amount of nitrate only, if there is in the system, then what will happen? Any diseases related to it you might have heard about, related to the oxygen carrying capacity of the blood. Anyone knows that name? Any guesses? So, okay. So the primary concern will be, it is known as the blue baby syndrome. Okay, it is called as the blue baby syndrome in infants. Why it is called like this, we will discuss. So the thing is, so whenever there is a high nitrate concentration, it will cause methanoglobemia. Okay, so this is the disease which reduces the oxygen carrying capacity in the blood, due to which a bluish skin can be observed in infants. So that's why it is called as a blue baby syndrome. Okay, and it is directly linked with the nitrate contaminated drinking water. If there are high amount of nitrates present in the water, this disease will happen, and it will primarily affect the infants. That's why it's called as blue baby syndrome. Okay, so this is the answer for the question. Many of you might be thinking about algal blooms. Yeah, it is there if all the nutrients are present, like nitrogen, phosphorus, then algal blooms will be the correct answer. But if you are thinking only in terms of nitrate, okay, then we should answer it as blue baby syndrome, right? We'll move forward. So the question is, what can you infer from the figures? So we have a graph here. So in the x-axis we have time, okay, in days, suppose, and in the y-axis, suppose we have some concentration. Here it is relative concentration, C by C naught. Like, what is the concentration with respect to the initial concentration? So C by C naught, just to make it dimensionless. But you can consider it as some concentration also. And the rate constant is also given, so it is constant, 0.5 per day. And we have two graphs, one for CSTR, one for PFR. So what can you infer? And it is talking about what is the removal rate in plug flow and CSTR. So in which case we are having higher removal rate. Anyone else? Just you can consider a particular time. Maybe you see at the stage of 5 days. Okay, at the stage of 5 days, what do you think, whether the concentration in CSTR is more or the concentration in PFR is more? And by judging that thing, you can say what is the which one is having higher removal rate. It's directly you can see. Okay, so as many of you are answering, it will be a plug flow reactor, which will be, so in general also we know that, as we discussed in question number 2, a plug flow reactor will be more efficient than a CSTR, right? So that is why the rate of removal will be higher, because it is more efficient. So for the same amount of time and for a constant K, okay, the removal rate of a PFR will be higher than the CSTR. So that's why that graph is going more downwards in the case of PFR as compared to the CSTR. So option 1 is correct. Okay, I think there is nothing to discuss much in this question. We'll move forward. Okay, so now a small numerical. It is similar to what we have discussed in the previous class. So a sewer carrying wastewater contains a compound X enters a nearby stream as shown in the figure. concentration of X in the wastewater is 250 milligram per liter. The stream has a naturally occurring X concentration of 50 milligram per liter. If the sewer flow rate is 0.5 meter cube per second and the stream flow rate is 2 meter cube per second, what is the concentration of X in the stream after the discharge point? Assume it to be a steady state conservative system. Okay. So similar problem we have done in the previous class. So please tell me the answer. Very simple calculation. I'll wait for a minute, then we can discuss. Anyone with the answer, please. I think calculator is also not required for this question. You can directly solve. I think if you are not able to solve, we will discuss it. Okay. Okay, so let's see the problem. This is question number 7. Yeah. So we have a stream, we have a river, I will say a river. Okay, and then there is some wastewater stream that is entering. Okay, so suppose QR is given as how much? It is given as 2 meter cube per second. That is the river, and the concentration is around 50 milligram per liter for that X compound. Okay, we don't know that compound, X compound. Then discharge of the wastewater is 0.5 meter cube per second, right? And C concentration of the wastewater is given as I think 250. Yeah, 250 milligram per liter. So this is the case. And what was the formula which I told you? And suppose this is the point of mixing. Okay, here the flow rate is QF and the concentration is CF. So what will be my QF? QF will be QR plus QWW. So both of things will add. So and CF we have to find out. So when we do mass balance, okay, mass balance per unit time if we do. So what is the formula I told you last time? That is QR into CR plus QWW into CWW will be equal to QF into CF. Right. So just input the values 2 into 50 plus 0.5 into 250 is equal to 2.5 into CF. So my CF will be, did anyone solve? My CF will be 90 milligram per liter. Very basic.
QF कैसे आया सर जी प्लस कर दिया आपने
Yes, yes. See, river water is flowing from here. The wastewater is flowing. So both will mix at this point, right? So we just have to add them. Flow rate will be mixed, right? Flow rate, it can't change. It will not reduce, it will not increase, because we have to see this section. After this section, what is the flow rate? So at this particular point, these both the streams are mixing together. So it will be adding. But concentration you cannot add just like that. You cannot add 50 plus 250 and tell 300. Okay, concentration is with respect to the flow rate. Okay, so the mass,
बट सर आई थिंक फ्लो रेट में विस्कोसिटी वाला कॉन्सेप्ट भी अप्लाई होगा.
viscosity, how? What viscosity concept? See, when we are talking about mass balance, okay, mass balance, what? So when we are multiplying Q into C, what is happening? What is Q? Q is nothing but meter cube per second, right? Meter cube per second. C is milligram per liter, or I can write it as meter cube per second into milligram. Liter also I can write it as meter cube, some meter cube. So meter cube will cancel. I am getting milligram per second, right? So this is what? This is mass per unit time, right? Mass per unit time. So what I am saying, for any particular time, this mass should be constant. Okay, suppose this is my river, this is the wastewater stream. Okay, I am dividing into two sections. This is section 1, this is section 2. So whatever mass of contaminant that is inside my mass per time of my section 1 should be equal to mass per time for that section 2. The mass cannot change because my system is a conservative system. Okay, nothing is getting degraded, nothing is getting added or deleted. Okay, it's like energy. Okay, you can transform into one part to another, but you cannot add or create or destroy anything. Okay, so here also I am saying that the mass of the contaminant X is not going to change over a period of time in section A and in section B. So that is the main ideology for this mass balance. That's why we are calling it as mass balance and multiplying Q into C. So we are getting the mass per unit time. Is it clear now? Okay. Okay. Others also, if you have any issues like this, you can stop me and ask. Okay. Okay, the next problem looks a little lengthy, but it's very simple, direct formula application. Okay, so just go through it. The flow rate through a reactor is Q meter cube per hour. Okay, the concentration of a compound in the inlet and the outlet are C in and C out respectively. The compound degradation allows first order kinetics. So first order degradation is happening. The mixing condition in the reactor can be varied such that the reactor becomes either completely mixed flow reactor or a plug flow reactor. So we have two conditions now. Everything is same, but in one reactor is CMFR or CSTR, other is a plug flow reactor. The length of the reactor can be adjusted as per the mixing condition. Okay, so the length can be LCMFR or it can be LPFR. Now, assuming a steady state, okay, and C out to C in ratio as 0.8, what will be my ratio of L of CMFR and PFR? Okay, just take a screenshot of this question. I will tell you what they are asking. Okay, just take a screenshot of this question. So in that question, they are saying that suppose there are two reactors. Okay, suppose there are two reactors. One is CSTR, one is PFR. Right now, the Q that is incoming in both the reactor, the discharge is Q. The incoming is seen. Here also incoming is seen. the outgoing is C out. Here also the outgoing is C out. And K value is also same. Okay, the degradation constant in both the thing, it is same. Okay. Now, for one, it is suppose L1, for the other one, it is L2. Okay. So what do you think? The length will be smaller or larger for the PFR? Which will have more length? Ideally, what should be the case? Any answer? Which reactor will have more length? PFR or CMFR? PFR will have more length. Just think about it. We have just discussed that a PFR is more efficient, right? We know that PFR is more efficient, and for similar conditions, if it is more efficient, that means the reactor size will be smaller. So if the reactor size is smaller, and if I am having the same cross-sectional area, the length will be smaller for the PFR. So suppose this L1 is for PFR and this L2 is for CMFR. So now we have to find a ratio of L2 by L1. This we have to find out. Okay, and it is given that what is given? C by C naught is equal to 0.8. This is given. What do you mean by C by C naught is equal to 0.8? Can you tell me? What do you mean by C by C naught is a point? So C is nothing but C out. Okay, C naught is nothing but C in, what I have shown in the figure. So what do you mean by this? C out by C in is equal to 0.8. How much? What is the percentage of degradation happening in the system? What is the percentage of degradation happening in the system? If my C out to C in ratio is 0.8, because these concepts will be required in the further questions. No, K is the rate of reaction. I am asking how much degradation happened for the pollutant. If my C out to C in ratio is 0.8, how much it has degraded? In percentage, you can tell me. What is 0.8? 0.8 is nothing but 80%, right? 0.8 is nothing but 80. So that means what we are saying? We are saying that C out is 80% of C in, right? That means whatever is coming out, it's 80% of the input. So how much is the degradation? 20%, right? So degradation is nothing but 20%. So that's what. So they are asking that for a degradation of 20%, what will be my ratio of L2 by L1? So this is what we have to find out. Anyone who knows how to approach this question? How to approach? Just you can unmute yourself and give an idea. How to approach this question? What we should find out ideally? Just try to think how we can approach this formula or this question. So for any CSTR or PFR, we have derived some equations, right? So what equations have we derived? We have derived equation for, any idea? For what we have derived the equation? So did we derive an equation for time? We have derived equation for TPFR, right? TPFR, TCMFR, we have derived. Okay, so using these terms only we will find out the answer. So I will solve it. Let's see. So so answer. So first for CMFR. Okay, so we have all derived this equation in the class, so you can go back to the class notes or through the lectures and see the derivation. Right now I'm just giving you the formulas. So for a CMFR, C, which is nothing but the C out, I would say C out is nothing but C in divided by 1 plus KT. So this is the formula, right? So now we know that C out by C in equal to 1 by 1 plus KT. Now in the question it is given as 0.8 is equal to 1 plus KT, right? Or if I uh, take this T out, so my T CMFR will be equal to 0.25 K. So this is my first. So in terms of K, my T CMFR, this T will be equal to 0.25 by K. Okay, so this is the first part. Now for PFR, so similar equation we have for PFR. So for PFR it is C out is equal to C in e to the power minus KT or TPFR. Okay, TPFR we can write. So this is the basic equation. So here also it again if we substitute the values it will be equal to e to the power minus k t PFR. Okay, so my t PFR will turn out to be 0.223 by k. So this was my first equation. This is my second equation. Is it clear till here? Anyone has any doubt? So these equations we have derived for a CMFR, for a PFR. Okay, these we have already derived in class. If you have any doubt, I can derive it once again. That is not an issue, but it will be a waste of time. You can go to the lectures directly and see the derivation. But to solve the problems, just you can make a note of these formulas, directly apply. No need to worry, directly apply these formulas because these derivations won't be asked in the exam. It is for your understanding. You just make a note of these formulas and try to solve the problem. Okay, so once we have this TCMFR and TPFR, so what we will do now for steady state, the velocity will be constant or not constant. Okay, so it will be constant. Now we have to find a ratio between L of LCMFR by LPFR. So the length we have to find out the ratio. So what will be my length is nothing but velocity into time. Here also velocity into time. So this will be TCMFR and this will be TPFR, right? So since it is constant, this will get cancelled. So it is nothing but ratio of TCMFR by TPFR. So we have these values. So TCMFR was 0. How much it was? 0.25 by K. This was 0.223 by K. So KK will get cancelled. We will get the answer as 1.12. So we can see the length of CMFR is to the length of PFR is 1.12. So that means CMFR length is more, which we expected. In the starting itself, we expected, right, that the length of this CMFR will be more. because it's a continuously stirred type reactor, whereas for the PFR it will be less. So here also we got the same thing. So logically also we have cross checked our question. Is it clear? Any doubt in this question? Anyone? No doubt? Shall we move forward? Okay. Based on your response, I am assuming that it's fine. Okay, fine. Okay, so 1.12 is the answer. Next question. The initial and the final DO after 5 days during a BOD test is given below. Find out the BOD in each of the case. Okay, so we have 4 different cases. You have to find the BOD for each of the case. So first one is, you just tell me, it can be done orally. So the first one is, initial DO was 8, final DO was 3. So what is the BOD?
5.
5. Directly 8 minus 3. So initial DO minus final DO. So 8 minus 3 is a 5. That is very okay. Good. So first value is 5. What about the next one? What is the answer for second?
0.2.
0.2. Okay. Anyone else? Any other answers?
Our analysis is not okay in option 2
Analysis is not okay. Okay. Why do you think so, Amit?
because the difference 2 से छोटा आ रहा है.
Yes. Yes. Exactly. That is the correct answer because result is not reliable. BOD cannot be determined. The final DO is almost equal to the initial DO. Okay, so we cannot rely on this BOD test. See, in the BOD test, there are so many variables. Okay, we have microorganisms, we have organic matter, it has to be put in a particular temperature for so many days, time, everything, many variables are there. Okay, plus a lot many chemicals are also there. Okay, so sometimes it may happen that uh, the microbes went to endogenous respiration. Okay, and they used some of the DO without consuming the organic matter, and there is some change in the DO. So we cannot trust that result, right? Or some leakage happened, more DO depletion happened, so that also we cannot rely on. So that's why if there is not much variation in the initial and final DO, we cannot trust the result. Okay, we have to redo it. Okay, C part, what will be the answer? Initial DO was 8, final DO was 0. So what will be my BOD?
फाइनल डीओ 0 नहीं हो सकती सर, कुछ ना कुछ तो वाटर में होगी.
No, that is not like true all the time. Suppose the microorganisms has used up all the DO, it will reach 0. It can be 0.
अगर 0 हो गई तो सर माइक्रोब्स जिंदा ही नहीं रह पाएंगे.
Microbes will not be able to sustain. That is okay. That is one way of thinking. But just think in terms of what is happening inside the BOD test. Okay, let's just discuss it further. So we have this BOD bottle, okay, and this is the cap. So inside this, what do we have? We have the organic matter. Okay, we have the microorganisms, and we have some dissolved oxygens, some nutrients also, but these are the basic things. So by BOD we are trying to find out how much organic matter is there. Okay, how much organic matter are there based on the change in DO. Okay, so we cannot count the organic matter, right? We cannot count the organic matter, but based on how the microorganisms are degrading this organic matter using this DO. Okay, we are calculating that change. How much DO is changing? Okay, so based on the change in DO, I am estimating my organic matter. Now suppose my organic matter was too high. Okay, it was too high in the BOD bottle, and the microorganism started degrading, and before 5 days, it used up all the DO. Okay, it used up all the DO, but still some organic matter is still pending. Okay, the microorganism needs some amount of DO to degrade the organic matter. Now the organic matter was so much that all the DO has been used up. That's why my final DO is 0 now. So will this give a correct representation? Suppose my organic matter was 500 milligram per liter, and it the DO was used up so much that still some 250 or maybe 25 milligram per liter is still remaining. Okay, but how will I know that? I cannot be certain, right? How much is still pending, how much has been used up? We cannot guarantee. So that means whenever my final DO is turning out to be 0 before 5 days, that test result we cannot accept. Is it clear to all of you? So based on your terms, based on in terms of DO, suppose my initial organic matter in terms of DO was 10 milligram per liter. Initial organic matter was 10 milligram per liter, but initial DO was only 8 milligram per liter. So within 5 days, it will use up all this 8 milligram per liter, but still 2 milligram per liter will still be remaining in the system, right? But this I cannot calculate. I am just assuming it to be 10 milligram per liter, but I don't know this value. This value is not known to me. So how will I be certain about that BOD test? We cannot be sure. So that's why whenever my DO is falling below 0, we cannot accept the reading. Is it clear to all of you? Okay. So that is the case. So C also we cannot validate. Now last one. Last one is also same. Here also the final DO it is showing little bit. Okay. So this also we should not rely upon. So always you should remember that the final DO should not be less than 2 milligram per liter. Okay, should not be less than 2 milligram. If it is going less than 2 milligram per liter, we cannot rely, because the microorganisms growth will be affected, as Amit has also pointed out. The microorganisms will not be able to sustain and perform to their full potential and the low DO regime. So that is also a case. So in both of the cases, we should not. So can someone tell me what we should do if my organic matter is too high, that it is using up all my DO? So what we should do to get the results correctly? Any idea? So now we know that my final DO range should be 8 to not even 8, 7 to 2. 2 to 7 if it is coming, then I can trust the BOD results. But many a times we will not get the final DO in between seeding or aeration. See, seeding is required when microorganisms are not present in the system. Okay, suppose you are doing BOD for a wastewater, no need of seeding. Okay, you don't have to do any seeding. It will automatically work. But suppose you have some industrial sample, okay, where you don't expect any microorganism, then we have to do seeding. So that is not the answer. I am saying if the organic content is more, very simple logic. If the organic content is more, my DO is getting used up, what I should do? In the BOD formula, what else is there not there? In the first question, we simply did 8 minus 3. One more term is missing. What is that term? Because in the question it is not mentioned. Dilution factor, yes. So dilution factor also you have to check. Suppose if the organic matter is getting used up, You dilute it 100 times. You dilute it 100 times and do the BOD test. You know that you have diluted it 100 times. So whatever result, suppose you are getting 5 milligram per liter, we will multiply with 100. So it will be 500 milligram per liter of BOD. So we have to do dilution. So always remember, whenever you are going to do BOD test, first do the COD test. COD test is much more easier to do. Okay, it is much faster. Okay, we can do it easily. So once we know the COD, we can, if it's a biological sample or it's a wastewater sample, we can trace back the BOD value, some 60-70% roughly. Okay, so if I'm talking about municipal wastewater, first do the COD. Suppose the COD is, I would say 500, okay, or 400. You find out the COD, it's very faster. Then you try to estimate the BOD. So 70-60% of 400 or 500. Okay, so 260, 280, that range it will come. So now you got an estimate of BOD. So now you know it is around 280. So this much BOD you cannot estimate by BOD bottle. So what you have to do, you have to dilute. So you dilute it 100 times or maybe 50 times and bring in the range of 2 to 5, 2 to 7 milligram per liter, that range. So once you have diluted, you got that range, now do the BOD test. So then your BOD test will never fail. Is it making any sense? Right? So this is how you have to do the BOD test. Okay, we will move forward. Okay, again, similar question in a CSTR, the concentration of the reactor is same as the concentration in the effluent of the reactor. Is it true or false? Answer it quickly. True, definitely true. We have discussed it again and again and again. So it is true. Okay, so dilution happens and the composition become identical everywhere because there is perfectly mixing condition. Okay, again a small numerical. Wastewater volume sample is 4 ml. Dilution water is 296 ml. Initial DO is 7.65. Final DO after 5 days at 20 degree is 4.24. KD is 0.23. Assume dilution water has no organic content. What is the BOD 5 of my wastewater? Please tell me. Please calculate and tell me. This is very simple. I think you should tell me the answer. What will be my BOD? 5. Yes, Amit is absolutely right. It is 255.75 milligram per liter. Perfect. So I'll just show it in the screen how to do. So nothing. BOD is equal to DO initial minus DO final into the dilution factor. So how the dilution factor will be calculated? That is the total volume divided by the sample volume. So total volume will be 4 plus 296, 300 ml, and the sample value is 4 ml. So this gives the dilutions. So you can see how much of dilution has been done. Okay, so roughly 75, yeah, 75 times dilution has been done. So see, for a BOD of 255, okay, which we came to know after this. So for a BOD of 255, 75 times dilutions have been done. So like whatever I discussed in the previous problem, the same thing. Okay, so same problem, next part. So same problem. Now next part is an estimate of the ultimate BOD of the wastewater. So now we have to find out the ultimate BOD. So please calculate one direct formula only. Everything is given. Any answer? Anyone who has joined today who was not there in the previous class? Are there anyone who was not there in the previous class? Okay. Just wait a minute. Okay, so I have shared a Google Sheet link. Okay, just open this link and fill in your details. Basic, your name, email ID, affiliation. Okay, just if I want to share any resources or any questions, anything data, okay, or any information related to the class, I will share with you directly to the through the mail. Okay, just fill in the Google Sheet. Okay, so we'll discuss how to solve. It is a direct application if none of you are able to solve it. So this is question number 12. So the formula for finding out the ultimate BOD is, so basic formula is BOD 5 is nothing but ultimate BOD, that is denoted by L naught, okay, into 1 minus e to the power minus kt. So this is the basic formula. Okay, so this time is in days, k in per day. So in the previous problem, we have found out the BOD 5 to be 255.75. We don't know the L naught. 1 minus e to the power minus k is given as 0.23. And since it is BOD 5, so into 5. Right? So L naught will be equal to 374.25 milligram per liter. Very simple, direct formula. Is it clear? Okay, very simple. Directly we can find out. Same thing has been given. Okay, next problem. Match the type of treatment with their primary function. So we have batch
इसमें से
reactor.
थोड़ा इसमें से थोड़ा बैक करिए सर, स्क्रीनशॉट लेना है.
Okay. Here just
ओके
keep a
सर.
note for that e to the power, it should be e to the power minus kt, okay? Not e minus 2.3 into 5. It should be in powers. I think some typo error happened. So it should be e to the power minus 0.23 into 5. Right? It should be in powers. Everything should be in powers. Or you can take a screenshot of this. Here I have written it correctly. This will be better. Okay. Anyway, you will get all these sessions recorded in the YouTube channel, so don't worry about it. Okay, so we have three types of reactor: batch reactor, PFR, and CSTR. We have to match with their primary function. Just tell me the correct answer. B. Yeah, very direct B. So for the batch reactor, you should always remember that there is no inflow or outflow from the system. It's a closed, completely closed system. We put in all everything, we close it, we run the reactor and then take out. Okay, there is no continuous inflow and outflow. Whereas a PFR, there is no mixing along the direction. Okay, there is it follows a plug-like mechanism, like n number of CSTRs are there, so there is no mixing in the direction of the fluid flow. And in CSTR there is a homogeneous reactor where there is both inflow and outflow. Okay, so pictorially also I have represented all the three reactors. Okay, next one. A wastewater stream is mixed with a river nearby. After mixing, formation of certain zone occurs. Which of the following zones is characterized by the highest level of treatment of pollutant? So is it the zone of degradation, zone of recovery, zone of clear water, or zone of active decomposition? This is a direct question. We have four different zones. Oh, this is not completed. Okay, then I think we will skip it for this time. I think these questions maybe in the next weeks it will come. Okay, then we will discuss in the next time. So don't worry about this. I will skip this question for now. We will discuss this after it is discussed. Okay, then we can discuss about this. The second stage BOD as shown in the figure is due to. This is discussed, I know. So what is this second? Is it some experimental error, nitrification demand, increased activity of bacteria, or interference of certain chemical reactions? So in the graph you can see first there is a hump of first stage BOD and then there is another hump for second stage BOD. So what is this second stage BOD? Nitrification demand, okay. Anyone else? So this is very direct. It is nitrification demand only, right? No, not B and C. Uh, C should not ideally cause a hump like that. Okay. So it should be nitrification demand. Okay. Now some numericals again. Though the question looks very big, but it's a one-liner. Okay, every answer is one-liner. So in a batch reactor, an experiment is run in the lab to remove the propionic acid. It is a common organic acid that is used in the production of various chemicals and is often present in the industrial waste stream. So no information till now. Initial concentration is 21 milligram per liter. Concentration after 30 minutes is 3.5 milligram per liter. That is the final concentration. Assume that the propionic acid can be removed by a process which can be described by first order reaction and assume steady state. For the given information above, estimate the rate of reaction. So you have to find K. So some informations are given. So first it is a batch reactor. Then initial concentration we have the final concentration, you have also the time, so you have to find out K. Just plug in the values and tell me the answer. Anyone with the answer? Okay, so for a batch reactor, generally what we will do, so simply we can say 0.583. Okay, yeah, it is close. 0. No, 0.05. Yeah, 0.05 is the correct answer. But actually it is 0.0597. Okay, so 0.06 it will turn out to be. And one more thing, if and also you have to see in what units they are asking the answer. Okay, so mostly if it is such a small value, they will ask in minutes. So what you are, oh, sorry, in seconds. Whatever you are getting is in minutes, so you can report it as in seconds. Okay, so basic formula, that is Ct is equal to C naught e to the power minus k t. Okay, so this is the basic formula. So here we have Ct as 3.5, we have C naught as 21 into e to the power minus k into 30 minutes. So we'll get the answer as k is equal to 0.0597. This is in minutes, okay, per minute. So if you report it in seconds, it will be 0.38 per second, right? So this is the answer. Okay, next problem. Since you have solved it, okay, the same thing I have just added. Now, keeping the question same, what they are saying, if the treatment system is plug flow, calculate the hydraulic retention time which would be required to achieve an effluent concentration of 1.5 milligram per liter with the same initial concentration in the experiment. So here we are saying that instead of a batch reactor, we are using a plug flow reactor. Okay, and now the effluent concentration is changing from 3.5 to 1.5, and the initial concentration is same. So what will be my time? So similar problem, just instead of K, we have to find out the T, or the hydraulic retention time, theta, in terms of theta we will say. Okay, so similar problem. Tell me the answer. So here you can keep the K value in per minute. Okay, that small 0.0597, because same K value will be used. Okay, so just keep the same K value. The answer you will get in will be in minutes. Anyone with the answer? Okay, so similar thing. Again, we will have. Okay, so question number 17. So just to differentiate between this batch and PFR, though both the equations are same, so I'm just writing it theta. So C theta will be equal to C naught e to the power minus k theta. So here theta represent the hydraulic retention time of PFR. Okay, so same formula. So here it is 1.5 is equal to 21 into k to the power minus 0.0597 into theta. So my theta will be equal to 44.2 minutes. Okay, so 44.2 minutes. Simple. Yeah, Haritra, it's right. Okay, next problem. Okay, again a small change. If the treatment system is completely mixed flow reactor, calculate the effluent concentration if the hydraulic retention time is 50 minutes. With the same initial concentration in the experiment, the effluent concentration is. So here they are telling that HRT we are giving it as 50 minutes. Okay, initial concentration is same, K value is same. What will be my effluent concentration? So tell me the effluent concentration. Here it's a mixed, a completely mixed flow reactor, not a PFR. 5.26, yes, Amit. Yeah, it is approximately correct. Okay, so we will just see for others. So here the formula will change as C theta will be equal to C naught by 1 plus K theta. So this is the equation. So we have C theta as, we have to find out C theta. C naught is 21, 1 plus 0.0597 into 50 minutes. Okay, so answer will be 5.27. Okay, very simple. Very simple. 5.2. Yeah, Haritra, it's correct. So this is how we have to do all these problems. Very simple. I will move forward quickly. Okay. A flowing river is an example of CSTR, CFSTR, plug flow reactor, batch reactor. This you can say directly. A flowing river. How does it resemble? C. Very simple. It's like a plug flow reactor. Okay. So nothing, it's a long, narrow channel. So it resembles a plug flow reactor. Which of the following represent the correct reagents for COD test? So we are talking about COD test. So which of them shows the correct reagents? So we have potassium dichromate, potassium chromate, sulfuric acid, silver nitrate, mercuric sulfate, silver sulfate. So many things are there. So you have to pick in the correct order. Not correct order, correct reagents. C. Okay. A and C. Any one will be correct. Okay, not both of them. So you are going on the right track. It is actually A. Okay, it is actually A. So we will see. So see, first this potassium dichromate will change this Cr6 plus to Cr3 plus. Okay, and there will be some amount of chlorides. Okay, so that can also interfere. So this also will be taken with by the potassium dichromate. Now HgSO4 HgSO4 will be required for precipitating the chloride. Okay, so to avoid the interference of the chloride, it will be like that, and then some amount of Ag is also required. So both Ag and HgSO4 are required for removing the interference. And sulfuric acid, like we have seen in the first two equations, there is some H plus because it has to be carried out in acidic medium. So for that, H2SO4 is required. Okay, so all the four are required. Next, steady flow is no change in velocity with distance, velocity changes with time, no change in flow rate with time in a stretch, flow rate changes with time. So what do you mean by steady flow? We have discussed in the initial problems, steady state or steady flow. C, yes, so it will be C, no change in the flow rate with time in a stretch. Okay, so based on the flow rate, we can, like, if it is not changing with time, so it's a steady flow. Next, when CH enters the river, the rapid depletion of dissolved oxygen is due to change in temperature, the suspended particles, the respiratory activity of aquatic plants, or the microbial activity. Why do the dissolved oxygen deplete? D. So it's a direct answer. It is D because of this microbial activity only. Okay. Only because of this microbial, they will use up this dissolved oxygen to degrade the organic matter. So it is that is known as biodegradation. So this is due to the microbial activity only. Okay. Next question. Which of the following represents the correct information about the Peclet number? So there is something called as the Peclet number. So we have some information given. P is equal to QL by AD or QD by AL or AL by QD. So various combinations are given. You have to find out which is the correct one. And P is either infinity 10 or 0 for PFR, or P is 0 or 1 or 100 for CSTR. So you have to tell me what is the correct information about the Peclet number. First option, anyone else? Okay, so actually the first option is correct. So P is equal to QL by AD, and P is infinity for PFR and 0 for CSTR. So this is the basic graph. So just if you want to remember about this Peclet number, always remember that, see, always remember that P is equal to QL by AD. So, and to remember this, always remember that Peclet number is a ratio of advection to dispersion. Okay, so always remember dispersion is denoted by D, so D will come in the denominator. Okay, and how advection is coming? So we know Q by A is nothing but U, so UL by D. So U will take care of advection part and D will take care of dispersion part. So it will be Peclet number. So now suppose you want to think about PFR. So PFR, the movement is happening in one direction. So one direction means it will be dominated by advection. Okay, just remember advection. So if it is dominated more and more and more by advection, that means what? Your denominator will be, numerator will be getting higher and higher and higher, and maybe tending to infinity. So that's why it is infinity for PFR and 0 for a CSTR. Because in CSTR, like it depends on the microbial degradation and all those things. So here you don't have to consider about advection and all. So it will be 0, right? Okay, now few more example problems are there. So you can try this out. Maybe this type you have already solved. I think we can go to some other problem. This you can solve. You can just take a screenshot and solve by yourself. It is similar to the previous problems which we have done. Just take a screenshot and maybe you can try to solve and cross check the answers. Okay. Next problem. Try to solve this one. Yeah. Little lengthy, but it will solve many concepts. Three CSTRs are in series, with the second reactor being twice the size of the first and third. So we have three reactors, 1, 2, 3. The second reactor is twice the size of 1 and 3. The pollutant concentration is 150 milligram per liter and flow rate is 400 liters per minute. The reaction rate constant is 0.007 per hour. Rate only depends on the pollutant. Calculate the removal efficiency of each of the reactor along with the corresponding HRT if the overall removal ratio is 80% desirable. Okay. So just take a screenshot of this problem. I will explain you what is happening. I hope you have taken the screenshot. So suppose there are three CSTRs. Okay. So this is 1, this is 2, this is 3. Now volume of V2 is twice of V1 or twice of V3, and V1 is equal to V3. Okay, so volume information is given, right? C naught, C naught, what is where is entering is 150 milligram per liter. So C naught is also given. Q that is entering is 400 liter per minute. Okay. K value throughout the systems is 0.007 per hour. Okay. And overall efficiency, eta overall is 80%. So that means if C naught is 150 is coming, this C3 I would say that is coming out from the third system is after 80% degradation. That means 20% of C naught is equal to 30 milligram per liter. Okay, so this much of information is given for the question. Now what you have to do, you have to find out the volume of V1, V2, V3 and the individual efficiencies of eta 1, eta 2 and eta 3. Okay, so this is the overall picture of this problem. Is it clear? Anyone has any confusion? Can you do it? Let me know if you have any problem. So, okay, to solve this, whatever concentration is coming out from 1, we will mark it as C1. That same C1 will be going into the second one. Whatever will be coming out will be C2. The same will be going into the third one, C2. And whatever is coming out, C3, or we can write it as CE, C effluent. Okay, C effluent we will write. That will be better. C effluent. So these are all the notations. Now simply we have to apply the formula for each of them. So what is the, for the first reactor, everything is CSTR. Okay, so CSTR formula we know, that is nothing but C out is equal to C naught by 1 plus kV by Q. This is the basic formula for all the CSTR. So what was the C out for 1? So that was C1 by C naught. I can write 1 plus 1 by kV by Q. Right? This I can write easily. This is equation 1. Now for the second reactor, what I can write? C2 by C1 is equal to 1 plus 1 by K. Now V is twice of other V's, so I can write 2V by Q. Right? So this is my equation number 2. Now for the third reactor, I can write CE, because what is coming out is CE by C2 is equal to 1 by 1 plus kV by Q. I can write it as 3. Okay. Now if I multiply 1 into 2 into 3, what will happen? C1 by C0 into C2 by C1 into CE by C2. So C1 C1 cancel, C2 C2 cancel. We will get only CE by C0. Right? We will only get CE by C0. And what about the other side? Other side will be equal to 1 will be the numerator, and we will have 1 plus, this term is twice, so square into 1 plus k. So this will be my overall term. Okay. So now we have to fill in the values. So CE was 30, C0 was 150, 1 by 1 plus kV was 0.007 into V we don't know, because volume we have to find out, V by Q was 400 liter per minute, or we can write 24,000 per hour, like that. Okay. Cos square 1 plus 0.007 into 2V divided by 24000, right? So this is the basic formula. From here we can calculate V. So V will turn out to be 1871962.61. It will come in liters, because we are, this Q value was in liter per minute or liter per hour, so it will be in liters. In meter cube it will be, so this is my answer. So V equal to V1 equal to V3 will be 1871.96 meter, whereas my V2 will be twice of V, so it will be 2 into, right? Simple. Till here everything is fine. Okay. Now we have found out the volumes. Now we have to find out the individual efficiencies for all the reactors, right? So what we will do? So we will, so first equation we will take. First equation was nothing but C1 by C0 is equal to 1 by 1 plus kV by Q. So C1 we don't know. C1 we don't know. C0 was 150. 1 by 1 plus 0.007 into 187,192.61 divided by 24,000. Okay, so I'll get C1 as 97 milligram per liter. So what will be my efficiency of first reactor? It will be 1 minus 97 by 150. So it will be 35.33%. Very simple. Directly we can find out. Now similarly you can do for the other two reactors. Okay, so I'll just give you the answers. You can cross check later. So C2 you will get it as 46 milligram per liter, and the efficiency of second reactor will be 52.577%. Okay, and C CE CE we know it as 30 milligram per liter. So efficiency of N3 we will get it as 35.33%. Okay, so similarly, just apply the same thing for this second equation and third equation. You will get the answer. Is it okay? Are you guys clear with this concept? Okay. If you are not able to understand, you can simply go through the question again. You can see the YouTube channel again. Okay, so one more question we'll do quickly. A 24-meter cube reactor operating in plug flow mode reduces BOD in wastewater from a value of 250 milligram per liter to 10 milligram per liter in a detention time of 10 hours. If the rate constant is 0.23 per day, find out the order of the reaction. So here every detail is given, but you don't know what is the order of reaction. Okay. So here you have to take care that whatever equations we have derived till now, mostly we have derived in terms of first order reaction. Okay. First order reaction. But here the order of the reaction is not given. You have to find out the order of the reaction. So for that, you should know the equations for each order, for a PFER, for a CSTR, everything. Okay, so for today, I will tell you the equations of all order reaction for a PFR. You can work it out for the CSTR also. If you have any doubt, you can get back to me. Okay, so we have to find out the order. So for finding out the order, we will just simply put in the values and see for which it is matching. If it is matching for that particular order, we will say the order is uh, the same. Okay, I will show you how to do this. Just take a screenshot of this question. Okay. So it is given that C naught is 250 milligram per liter. Okay, and CE is 10 milligram per liter, and K value is given as 0.23 per day, and time is given as 10 hours. So we have basic equation with CE, C naught, K and T, right? We have basic equation having all these four terms. So what we will do, we will put in the values of C naught, K and T in the equation, and we will see if we are getting the correct CE value or not. Okay, this is how we have to do it to find out the order. Now, for any PFR, just note it down. For n is equal to 0, that is for zeroth order reaction, the equation is C minus C is equal to, just a minute, C is equal to C naught minus K into HRT. So this is for zeroth order reaction. For first order reaction, it is, we have already derived it, C is equal to C naught into e to the power minus K into HRT. So this is the first order reaction. For the second order reaction, it is 1 by CE is equal to 1 by C naught plus K into HRT. Okay. So these are the known equations. So now we will just simply put and see. Okay. So for the first condition, C naught, if I put 250 minus 0.23 into 10, how much I will get? I will get it as something 249.9 milligram per liter, which is not equal to 10, right? So it is not zeroth order reaction. Okay, next one we will put again we will put in the values. So the answer will turn out to be 227.15. So this is also not correct because it should be equal to 10. For the third one, if you put in the values, we will get CE as 0.10.01 something. So this is right. So our order of the reaction is 2. So it's a second order reaction. Okay, second order reaction. So this is how we have to do. Is it clear? So like this, I have given you the equations for PFR for 0, 1 and 2. You can try to find out the equation for CSTR. Okay, for 0, 1 and 2. More than 2 is not required. Up to 2 degree only. So up to second order only they will be asking most of the time. Right? Okay. So that's all. So these many questions I had for today. And we'll meet again on 11th February, same on Tuesday from 7 to 9 p.m. And this is my contact me email ID saha19akash. So it's written there saha19akash @gmail.com. Okay. So if you have any doubts or any clarification, you can send a mail to me. Okay. Anything else? If you don't have any doubts, you are fine. You can leave the session. That's all from my side for today. I hope you are able to follow the lecture. If you want me to solve some other type of problems also, please let me know before the class so that I will try to incorporate in that week's lecture. Or if you want me to go through one concept again, some particular concepts related to that week's module, you can let me know. I will discuss in the class. Right? So if you don't have any further doubts or clarification, yeah, you please share it over the email. And please tell me what is your problem and which part you are struggling, because I may not be giving you the answer, because uh, I should not give you the answers for the assignment problems. Okay, I can help you, but I should not give you the answers. So just let me know where you are facing the problem, which part. I will try to help you. Apart from that, any other question is there, I will try to help you. But particularly for assignment problems, I may not be able to give you the answer. Right? Okay, then you can leave the session if you are done.